Okay, the next feature relates to complex source summation. That is, being able to, in post-processing, after the simulation is run, to add up different or responses from different sources, sort of after the fact. And this obviously is very important for analyzing, for example, PA systems in space and just the combined response in a room from many sound sources. And I want to start by demonstrating this at the very kind of fundamental level, just to showcase some of the nuances around this. And then I will move to a very large and complex case and show it also in action in kind of more practical setting. So I've set up here a very simple simulation, which is essentially a free field simulation because it's a very big box and I just simulated a short amount of time. There's one receiver and kind of two sources, a bit different distance from the receiver. And we see this kind of pulse from the two sources fly by this receiver, and that's all we have in the response here. And in the frequency domain, this looks something like this. It's an omni source with just a flat spectrum. So we can see here the level of the two sources and the same amplitude across all frequencies. This was a hybrid simulation where the wave-based was up to 750 Hertz. Now I'm going to sum the response from these two sources. I would do that by simply clicking Sum Sources here, check these sources that I want to sum. These can be as many sources as I want. Click the Sum button, takes a couple of seconds, and then I get back a new source which is summed. I've already done it here just for saving time. So what we see here, if we look at the summed response, we see here this strong comb filtering effect from the two waves interfering at certain frequencies, kind of in a destructive way, to reducing the amplitude and increasing the amplitude, constructive interference at other frequencies. And this kind of highlights the sort of phase-based nature of both treble solvers, both the wave-based but also geometrical acoustics. You see here, this is where the transition frequency is, that it just kind of very seamlessly preserves the phase as it goes from the wave-based over to geometrical acoustics. So this kind of shows how you could, obviously it's just some sources, but also kind of how this intricate nature of the different contributions are preserved across the frequency range. This was at the very most fundamental level. Let me quickly show you another similar fundamental case, just not in free field, but actually closer to a boundary, so we just see like a single reflection. We can see the direct sound and then a single reflection. And I've simulated this for two different material properties, one which is just a flat 50% absorption, and another one which has some glass wool properties, which will have different absorption properties, but also different phase properties. And I'm trying to show you here that if we then look at the response of these two different reflections, or the same reflection but hitting a different type of material, we see that the positions of the peaks and dips has been changed because of the phase response of the material. So this is just to highlight the kind of, again, the phase-based nature of treble and the improved accuracy you get for example, very important early reflection modeling and oralization for perceptual quality and so on. And then this certainly kind of continues if we would look at summed sources. So here for these two cases of the different materials, we see if I have two sources and kind of hitting this wall and being reflected back, the frequency response is actually quite different due to both the amplitude response and the phase response at the boundary. So this was maybe quite detailed and acoustics nerdism, but it's just to highlight that materials are modeled in a more precise way than what has been typically done in the past in treble, preserving not just absorption but also phase properties and also in the solvers themselves. Okay, now that was kind of very academic or sort of theoretical. Let's now look at a real case where we're going to sum a lot of sources. So I'm going to open a project here, which is called Train Station in Oslo. And this is a large model. It's around 30,000 cubic meters. And I've put in here 72 sound sources into the model. I've put these tannoy ceiling speakers all across the model. I'm going to hide the surface receiver so you see a bit better. So all across this model here are these ceiling speakers. So this would be a rather typical scenario of modeling a large infrastructure project like a train station or an airport or something like this, and making sure that the PA system can be heard. And I have, as I said, put in 72 of these sound sources. I put in a few listening positions if I wanted to do oralization, and then I put this very large surface receiver as well, which has around 1,000 grid points on it. And I've simulated this for 2 acoustic conditions, just for fun, as always, kind of more acoustic treatment, less acoustic treatment, so we can compare some results later. This kind of simulation takes around 5 minutes to run in Treble for all the sources in this grid receiver. We tried running this in another kind of legacy acoustic simulation software. It took more than 10 hours there, so this is a great example of the kind of drastic speed up and workflow efficiencies you can get with using Treble, because it all runs in the cloud, it all runs in parallel, and so on. So and you can very quickly then iterate on designs of these kinds of projects. So let's take a look at the results. I've pre-run it once again just to save a little bit of time. And I am going to show you first maybe just these 2 conditions that I simulated. So one which I called reverberant V2, I was doing some iterations, has a reverberation time up to around 3 seconds in the mid-frequency range, whereas just over 1 second this treated case here. But I mainly want to look at these surface receivers and look at the combined response of this massive PA system that we have set up here. And I can, for example, look at sound pressure level here from a single source that we see kind of spread across the space, or the speech intelligibility that I can see how it varies across the space. But more interestingly, I can look at the combined response. And I've already clicked some multiple sources and then clicked this guy here, which selects all of them, ran it, took a couple of minutes, I got back this summed source, which I called all sources. And by the way, while source summing is happening, I can, as with everything in Treble, I can just kind of leave it running in the cloud and go work on something else meanwhile. And let's compare the results here from this PA system between the 2 simulations. So overall, we certainly see that the speech intelligibility is lower in this reverberant condition compared to the treated condition, perhaps especially in this region here. We can, for example, investigate, let's see which areas have speech intelligibility higher than 0.5. See, that's quite well covered in this design I made of the PA system earlier, whereas this part here does not reach 0.5 in this kind of more reverberant condition. So I think this has kind of illustrated in a nice way the source summing capabilities, which we are launching now, but also kind of showing Treble in action on a very large project and how efficiently it can run on such cases. Before I wrap up my talks about source summing, I want to go back to the studio model I was showing you earlier and just quickly show you in the modal view how I can, of course, also sum sources there and look at the mode response from while 2 sources are exciting the room. Select from the same simulation, the one I called with treatment, and I'm going to compare one subwoofer versus the summed response from both subwoofers. I'm going to set the range here so it's the same when I'm flipping between the 2, just to kind of be consistent. And then we can see here, this is sort of my take on it, not being an expert studio designer, but it appears to me that The response is a bit more even across the space at low frequencies when we have the two subs compared to the one. So if I sort of scroll around here, certainly there are dips and peaks, but it's still somewhat sort of bit more uniform, whereas if I look at the single one, and especially sort of this part of the model, yeah, seems less covered somehow at low frequencies. But this is indeed for the designer to analyze and so on, and we're bringing the tools to be able to do that.